Welcome. Let us continue with our review of some principles in thermodynamics that we started in the previous lecture. Now, let us look at the three laws that you would have already studied, the three laws of thermodynamics. The zeroth law first. If the zeroth law states that if two systems, let us say x and y, are in thermal equilibrium with a third system z, okay, then they are also in thermal equilibrium with each other. It is a very simple statement and it is actually a truism. I really cannot go about proving it by other means. To repeat, there are two systems, let us call them x and y. If they are in thermal equilibrium with each other, with the third system, let us say z, then they are also in thermal equilibrium with each other. This zeroth law actually provides the basis for temperature measurement, okay, as it is shown here. This is the substance x or the system x, this is the system y, and they are individually in thermal equilibrium with the z here, okay. The z is the thermometer which is used to measure the temperature of x or of y. If x is in thermal equilibrium with z and y is also in thermal equilibrium with z, then x and y are in thermal equilibrium with each other. Let us consider the condition that we just said, x in thermal equilibrium with z and y in thermal equilibrium with z, okay. Which means that the reading on the thermometer would be the same, and therefore the equality of temperature measured on the basis of thermal equilibrium between the system and the thermometer is the criterion for thermal equilibrium between the two systems, say x and y. Therefore temperature T can be considered a consequence of the zeroth law of thermodynamics, and it is the one that determines thermal equilibrium. Now let us look at first law. The first law is nothing but the law of conservation of energy. The changes in many forms of energy are essentially equated to one another in the first law. There is nothing more to first law. Typically the changes in the energies of the system parts are equated to each other. For example, the changes in the energies of the system internals are equated to the changes in the energies of the system that cross the system boundaries. This is a system that is indicated by the dotted line here. The energies that cross the system boundaries, these two are coming in and this is going out and so on. The changes in energy inside the system is related to the changes that cross the system boundaries. There are two forms of energies that cross the system boundaries, or the forms of energies that cross the system boundaries are actually divided into two categories, heat and work. Why do we need to divide these into two categories, heat and work? It's essentially because heat and work are not completely interconvertible. You cannot convert heat into work completely, and therefore you need to consider them as two separate entities. To understand this a little better, let us slightly jump ahead. Okay, we are going to look at this later, but since this is a review, you have already looked at it, we can jump ahead to understand this a little better. The Clausius statement of the second law is as follows: it is impossible to make a transfer of heat from a heat bath at uniform temperature and obtain an equivalent amount of work without causing a change in the thermodynamic state of some other body. Okay, that is a complete statement of the second law. Let me read it again to get it across a little better. It is impossible to make a transfer of heat from a heat bath at the uniform temperature and obtain an equivalent amount of work without causing a change in the thermodynamic state of some other body. The efficiency of such a process is given by work obtained by heat input, and you would have already seen in the previous classes that can be related to 1 minus the ratio of the surroundings temperature to the system temperature. The efficiency can reach 1 only when the surrounding temperature is 0 Kelvin. If you recall, these temperatures are in Kelvin, okay, and reaching 0 Kelvin is impractical, and therefore it is impossible to completely convert heat into work, and that is the reason we need to consider them as two separate quantities. The useful forms of the first law, for us at least, is to begin with when it is applied to a closed system. For a closed system, when there are negligible changes in other kinds of energies such as potential energies, kinetic energies, surface energies, magnetic energies, and other kinds of energies, then you can relate the change in the internal energy delta U to the heat interaction across the system boundaries and the work interaction across the system boundaries. Delta U equals Q minus W is a useful statement of the first law for us. This delta U is the change that occurs inside the system. Q and W are the energy interactions across the system boundaries. What happens inside is being related to what crosses the system boundaries. For a differential process, we can write the first law as du equals dq minus dw, where these d represent the differentials. Therefore, internal energy U can be considered as a consequence of the first law of thermodynamics. It essentially determines the algebraic sum of the heat and work interactions in a process, or heat and work interactions for a system. We also need to understand what state and path functions are very clearly. You would have learnt that the internal energy is a state function. In other words, its value depends only on the state of the system, irrespective of the path followed to reach that state. For example, if the system is undergoing a process from state 1 to state 2, whether the path of the process is one way or the other way and so on and so forth, as by path we mean the set of intensive variables changing and so on and so forth, whether the path is one or the other, as long as it is a state function, the value of that function depends only on the state of the system. The value of internal energy at state 1 would be the same, and the value of internal energy at state 2 would be the same irrespective of the path taken to reach 2 from 1. Whereas the heat interaction across the system boundary and the work interaction across the system boundary are path functions whose values depend on the path taken during the process. This is a very important concept. In fact, we will be visiting this again and again, and at an appropriate time I will tell you an important aspect of this which helps us significantly in developing relationships in thermodynamics. Now let us look at second law. The second law can be stated in many different ways, and one of the statements is as follows: natural processes can never be completely reversed, is one way of stating it. More formally, the entropy of a system in an adiabatic enclosure can never decrease. It remains constant in a reversible process and it increases in an irreversible process. That is another formal way of stating it. The entropy of the system, as you would know already, is defined as ds equals dq by t in a reversible process. As you know, q is a path function Therefore, dq reversible by T is a way of defining entropy ds. Entropy is a state function and an extensive property. State function, it depends only on the state of the system and not on the path taken to reach the system. Extensive property means that more the amount of material there, higher the value of the property. If a system and its surroundings can be considered to be in an adiabatic enclosure, very important, please note this. If the system and its surroundings can be considered to be in an adiabatic enclosure, application of the second law gives us that the entropy of the system of both the system and the surroundings always increases in a real process. Now, the universe itself can be taken to be in an adiabatic enclosure because the universe contains everything, okay, there is nothing beyond the universe. So, the whole thing can be considered to be in an adiabatic enclosure, which means there is no heat interaction. For the universe as a whole, the entropy of the universe always increases. You can state this mathematically as the changes in entropy of the system plus the changes in entropy of its surroundings should always be greater than or equal to 0, and if we want to replace this by an equality, we say that the change in entropy of the system, ds of the system and ds of the surroundings equals d epsilon. D epsilon is the amount of energy that is generated during the process. It is of course 0 for a reversible process, as we know, as we saw earlier in the definition of the reversible process, and positive for a normal or an irreversible process. A natural process occurs in the direction of increasing entropy. We have already seen that if you take the entire universe as a system, the entropy of the system has to increase. As long as we have an expanding universe, the natural process will always happen in the direction of increasing entropy. The water in a waterfall will always fall down and never spontaneously go up, and the entropy provides us with a measure to predict whether the water will flow down, to tell that the water will flow down spontaneously, always flow down spontaneously. Entropy can also be interpreted as a measure of the disorder in the system. It is a concept, order, disorder, order everything nice and packed and so on and so forth, disorder not so packed, random, not so ordered. The biological cell, as we all know, is highly organized, right? There are many processes taking place in it, but the biological cell itself is highly organized. Does the biological cell contradict the second law? The answer is it does not. Okay, so far we haven't come across something that violates second law. That is because of the following reason. The second law is applicable to a system in an adiabatic enclosure, or if you take the system and surroundings as a whole, which can be considered in an adiabatic enclosure at all times. Therefore, although the entropy of the biological cell decreases as implied in the higher order in a biological system, the overall entropy of the cell and the rest of the universe increases during a cellular process, and therefore the second law is not violated. Entropy S, entropy as indicated by the letter S, denoted by the letter S, can be considered as a consequence of the second law of thermodynamics. It determines which state succeeds the other state. Now let us look at what continuum means. We said that a continuum is essential for the application of classical thermodynamics, and therefore let us see what a continuum actually means. The continuum is a situation when there are a large number of unitary particles, they could be molecules say, per unit volume, and the substance under consideration can be considered as a continuous one. Okay. That's saying it in words, but what does it actually mean? It's something like this. If you look at a plot of density, okay, this is the density here given here, and this is the density at a point in an enclosure that's containing a gas, let us say. And let us say this x-axis gives you the number of gas molecules in the enclosure. If the number of gas molecules are large and you're measuring the density at a point, then the gas is a normal gas, the properties are dependent on pressure, temperature, and so on. Therefore, you expect the density of the gas to be reasonably constant. That's this region here. Okay. And by doing this, I mean we are reducing the number of gas molecules in that enclosure as we go from here to here, say by pumping out through using a vacuum pump or something like that. When you reach a certain point, the density at that point is going to start to vary, because the mean free path of the gas molecules is not going to be representative of the normal gas conditions. The number of molecules have become so small per, let's say, unit volume, that the mean free path and other aspects are not going to be appropriate to consider it as a continuous gas. And therefore, the density at the point is going to vary significantly, and the variation is going to go up and up as you reduce the number of molecules more and more in the curriculum. The number of molecules are actually going to go on reducing in the enclosure, less and less number of molecules in the enclosure. This part where, let's say, the properties are continuous, the mean free path is appropriate as given in a normal gas and so on and so forth. Mean free path is the distance traveled by the molecules before an average collision. This is the region where the continuum is applicable, or this is the continuum region. This is the region where classical thermodynamics is applicable. Classical thermodynamics is not applicable in this region where the principle of continuum is not applicable. However, the statistical thermodynamics is applicable over the entire region, and that part will be taken up in the last 10 hours of this course by Professor Sanjeev Senapati. Okay. I think this is good enough review. Yeah, just to make it formal, distance traveled by a molecule before it hits another molecule, that's the mean free path, is much longer than the standard mean free path of the gas, and that is what happens in this region where you need statistical thermodynamics. And statistical thermodynamics principles are highly useful in analyzing, understanding interactions between biological molecules, DNA, protein, and so on and so forth, things like that. So that's the reason why it is important to know this at an undergraduate level. I think this information is whatever we have covered over the past 2 lectures is good enough as a review of the background information. When we begin the next lecture, we'll get into the actual material for this course.